Kaletha from Princeton, and this title is Endoscopic Transfer of Depth 0, Suprcuspidal Endoscopic.
Well, thank you very much for the invitation. So title is already on. So let me start with just a little bit of notation. We let F be a p-adic field with ring of integers. And we're going to say gamma is going to be the absolute Galois group. We have the Weil group with its inertia subgroup and wild inertia. And we're going to take G to be connected reductive F group, and G sub RS is going to be the Zariski open-dense subset of strongly regular semi-simple elements. These are those whose centralizer is a maximal torus. And so one point of departure in the theory of endoscopy is the fact that when we look at this set of strongly regular semi-simple elements, that there are two equivalence relations one can put on this set. So one can look at conjugacy under either the F bar points, and this is called stable conjugacy, or under just the F points, and this is called rational conjugacy. And somehow the observation is that in general those two equivalence relations don't agree, that this is a broader equivalence relation than this one. And a simple example is just in SO2F. If you look at the matrices AB epsilon BA and A pi inverse B epsilon pi B A, where pi is a uniformizer and epsilon is a unit which is not a square. And so what is happening is that each stable class in here is going to decompose into some number of rational conjugacy classes. It's known that this number is finite. And so stable conjugacy is a grouping of normal conjugacy classes into finite sets. And from the theory of finite groups, I guess one has the philosophy that conjugacy classes correspond to irreducible representations. Somehow one expects some kind of a rough philosophy like this to work also for p-adic groups. And in particular, if you have a grouping like this of conjugacy classes into finite sets, we expect to see a reflection of this situation on the spectral side in some kind of a grouping of irreducible representations into finite sets. And those irreducible representations are called L packets. And I want to remind the audience of a few conjectural properties of these L packets. So these L packets are supposed to be parameterized by the so-called local Langlands correspondence, which is a bijection like this. And it's partly a reminder and partly just fixing a notation for the symbols that we'll be using in a bit. And in order to save a little bit of notation, I'm going to focus only on L packets consisting of supracuspidal representations. And so what we have on this side is these are going to be well, they're going to be homomorphisms from the Weil group into the L group, and the brackets here denote conjugation by G hat. So I'm taking the Weil form of the L group. So these are going to be homomorphisms which are sections of the natural projection from the L group down to WF, and they're going to have semi-simple image. And moreover, they're going to have the property that the centralizer of the image of this homomorphism by G hat is going to, it always contains the gamma fixed points of the center but we expect that the gamma fixed points under center are contained as a subgroup of finite index. And so this is the expectation of parametrization like this, but there is also an expected parametrization of the constituents inside each of those finite set. And I want to assume for now that G is quasi-split, just to get us going, but then later it will be important that we relax this condition, and we want to actually take care of all possible G's, not just the quasi-split ones. But for now, G is quasi-split. Then what one wants, what one expects is the following. We're going to look at the following finite group. Well, this is basically this quotient here. We're going to take the centralizer phi and G hat, and we're going to mod out the center of G hat with the Galois fixed points of the center. And then the expectation is that there is a bijection from the set of irreducible representations of this finite group onto this finite set. Okay, so that's the expectation. And the philosophy was that on the geometric side we have grouping of conjugacy classes into stable conjugacy classes. On the spectral side we have grouping of representations into finite sets. But there is not just that's not just a philosophical relationship. There is actually formal properties which underline this relationship. And the first formal property is the following. We can, using this bijection, we can form a certain linear combination of characters namely, we can sum over elements of the left-hand side, and then we can sum up the characters of the corresponding representations. Let me denote this bijection by rho goes to pi rho. But we do a certain weighting of these characters. In fact, in the situation that we'll be dealing with at some point, this group will be abelian, so it will be literally just taking the sum. Here, more generally, one takes this weighted sum, and that the conjecture is that this, which I want to denote by S theta phi, is a stable, let's say, function. And stable function means it's a priori it's a function which is constant on conjugacy classes because each summand is, but it's supposed to be actually constant on stable conjugacy classes. So this is the first really formal statement that connects the grouping on the geometric and the grouping on the spectral side. And the second connection is a bit more subtle, but it's actually the topic of the talk. And this is the so-called endoscopic transfer, which I would like to say a few words about. So given that we have this bijection, we can form other linear combinations of characters inside the out packet. So if we give ourselves an element in the centralizer, which is semi-simple, then we can form another linear combination, which is some kind of an alternating linear combination. And I'm going to call this the S unstable character. We're again summing over the same set, but now we're taking the characters of the representations on this finite group, evaluated at the element S, and those will be the weighting factors. Now this is, of course, the way it's done, not going to be stable, but it was one of Langlands' insights that it is going to be related to a stable function on a different group, and that different group is the endoscopic group. Now, so how do we get the endoscopic group? I want to illustrate this first in a somewhat simplified example just to get the idea across and then say what happens in general. So simplified is, let's assume two things. One is that G is split, and the other is that the centralizer of S in G hat is connected. I mean, these are unreasonable assumptions, but let's make them for, I mean, unreasonable because it, you know, that it just won't happen very often. But let's just make these assumptions for a bit, and let's call this H hat. So H hat by duality corresponds to a unique H, which is a split F group. And moreover, so what do we have? Well, the Langlands parameter is now a product of two homomorphisms. The L group is just a direct product now of G hat and the V group, and such a homomorphism is a product of two homomorphisms, the identity homomorphism here and some homomorphism here. And just by the way we constructed everything, it's tautological that we get a factoring like this, that the image of our Langlands, we took S, which centralizes everything in the image, and then we took everything that centralized that S, in particular the image will be in there. So that's a tautology, but if we believe in the local Langlands correspondence, this tautology dually gives us something quite interesting, namely it provides us with an L packet for this group H now. And so given phi and S, we get 2 bits of data. We get the unstable character on G, and we also get the stable character of this new L packet, which is now on H. And so the hope is that these are related. Now this is extremely vague, but I'll say precisely what this means in a minute. But I first want to drop these weird assumptions that we made here. So we're going to unassume these now and say in general, and there is an interesting phenomenon that occurs in general. The H hat is going to still be pretty much the same as what it was before, only now we're taking the connected component. But we need a second piece of data which we can get out of this, and that's we're going to call script H. This is just the product of H hat and the image of the Langlands parameter, and this product is taking place in the L group. And one can see quickly that what one gets out of this is an extension like that of the V group by H hat. Now, what does this extension give you? Well, it gives us a homomorphism from the V group into the auto-automorphisms group of H hat. Just take an element, lift it here, let it act on here, and up to inner automorphism, this is well defined. And if we take, again, the unique split F group, which is dual to this, then we have a canonical isomorphism. I want to call this unique split group like this, and we're not going to use it at all, but this is what it is. And what this homomorphism gives us is a unique quasi-split outer twisting of this split group. So this homomorphism provides us with a quasi-split F group. Okay? And what we have now is we have a similar situation, but not quite similar, because there is one additional thing that's happening. So what we have here is, first of all, we get, of course, just again by construction, the same kind of factoring, only now that our Langlands parameter factors through this script H against tautologically. But the point is now that what the script H was an extension like this, and the L group of H is also an extension like this, and we would like to have a Langlands parameter for H. We'd like to have a homomorphism into the L group of H. But it's not in general true that these two extensions are isomorphic. This is not really something to worry about too much. There is, there is a one can do something, but it's interesting that in the situation in which we'll be in, namely where our groups are going to be unramified, these two extensions are in fact isomorphic. And so since we'll be interested in the unramified case, I can just take, and this is going to be a choice, an isomorphism from here to LH. So this isomorphism is if GH unramified and is due to Hales. And so choosing this isomorphism gives us now the following. First of all, we have, again, a Langlands parameter for H. But second of all, and this is also an important bit of the data, is we have an L embedding of the L group of H into the L group of G. So what we get is, well, we had H and S, and I want to call this L eta. So L eta is the embedding from LH into LG. And this is an extended endoscopic triple. And moreover, we again get the stable character on H. And again, the hope is the same, that this thing is related to the S unstable character, like up here, in some way that we now can specify. So get this on H, and we hope that this is related to the S unstable character, like that.
So do you have a canonical choice when they are under?
No, you mean here? I don't think that the choice is canonical, and this is why you keep track of what you're doing here as well. And this will play a role when we normalize transfer factors, which is what we're going to do now. You can always, I mean, any such L embedding you can fudge around with by multiplying by co-cycles to the center of H. And this will have then the role of changing the whole transfer by multiplying everything with the global character on H. Okay, so now we have all the data we need. We have the distributions that we would like to relate. What does it mean to relate them? Well, so the first bit, the important object that we need is provided by the theory of Langlands and Schallstadt on transfer factors. So what is a transfer factor? Well, it's a function like this. So it's a function in two variables. It takes a strongly irregular semi-simple element on G and elements on H which are even slightly more regular than strongly regular. And this makes sense by the relation of H and G. These are somehow G strongly regular. Whatever it is still a Zariski open dense subset. And so this function tells you, the crudest thing that this function tells you is when two such elements are related. It's going to be non-zero when these elements are related, but it has actually much more subtle information than this. So I want to just give a few basic properties. So this is invariant in gamma under conjugation and in gamma H under stable conjugation. Did I put a cross again? I'm sorry. Of course, this function should have the urge to put zeros as when it wants to. When these things are, I mean, it should be zero for most of the time. But definitely, thanks. So there is one important point which we'll discuss later on, and that's the fact that this function is not canonically given. It's given only up to a non-zero scalar multiple. And so the question will become, well, how do we choose a good normalization? But let's ignore this for now and just say that we have picked some normalization and see what we do with this. Well, so now we give ourselves such a sufficiently regular element in here, and so what we can do is, first of all, if we have a function which is smooth with compact support on H, we can just form its stable orbital integral at gamma H. If you haven't heard this, this is just exactly what it says. You're integrating this function over the whole stable conjugacy class. And if we have a function, same kind of function but on G, we can form, I want to call this the delta orbital integral, because it depends on the choice we made there. And this is going to be the following sum. We're summing over all elements in GF up to conjugacy, and we're using delta to put weights in front of the orbital integrals, which are, again, here we're just integrating f over the conjugacy class of gamma. We're summing all those integrals, but we're putting these weighting factors in front. In particular, I mean, these weighting factors will be non-zero for only finitely many conjugacy classes, so this makes sense. And so now the very deep theorem, due to many people, I'll try to list a few, and the list will probably not be exhaustive. But so it's work of Langlands, Shellstadt, and there is no particular ordering as well. Kottwitz, Hales, Vautz-Pourget, and Go. And so this theorem, which you may call geometric endoscopic transfer, tells you that for every f there exists some f upper h such that these two functions in gamma lower h are equal. Okay. And so with this now we can just finally say what it means for this, what this hope is, what it means for those two distributions to be related. Maybe I'll leave this picture here a little bit. And so now the conjecture is that what do we have? Well, we have this unstable character corresponding to the L packet for phi, and we can treat this character as a distribution. You know, usually in p-adic analysis, people think of, or in p-adic representation theory, people may think of characters as functions, but they're actually even more naturally defined as distributions. So when we feed f to this distribution, we expect this to be equal to the stable character for phi h fed with f upper h. So this is what it means for these two to be related. And now let's step back and look a little bit at normalizations. FH is not unique. Its stable orbital integrals are unique, and you can modify it by any function whose stable orbital integrals vanish.
The conjecture is about any of these transfers.
Exactly, but the point is somehow that yes. So the point is that one of the previous conjectures said that this distribution here, or this function, is stable. And what that means is that its value on f upper h depends on it only through the stable orbital integrals. So there is no ambiguity in this situation. But so what we have here is, well, so in order to integrate here, we need some Haar measure on h. In order to form here, we need the normalization of the transfer factor, which we chose, and some Haar measure on G. So those are 3 bits of data on which f upper h is going to depend. If we change the measure here or the measure here or the delta, the corresponding scalars are going to be tagged on f upper h. Now the Haar measures are completely irrelevant because those two distributions also depend on them in their definition. And so whatever change you make in them cancels. But what doesn't cancel is the dependence on the particular choice of the transfer factor. So this conjecture as it stands is not really well defined, because if you change delta, you're going to change this side by a scalar, and this side is not going to change. So there has to be a particular normalization of delta that makes this work. And so here it is. So remember, we're still assuming that G is quasi-split. And so in this particular case, there is a nice normalization of the transfer factor due to Kottwitz and Schellstadt, and it's called the Whittaker normalization. So, and it depends on a choice. So choosing a pair B psi, where B is Borel defined over F, and psi is a character on the unipotent radical of this Borel. And it's a character which is generic. So what this means is that it doesn't vanish on any relative root subgroup. So given such, or not choosing, but given such data, we obtain a canonical normalization of this transfer factor, which is called the Whittaker normalization. And this is the normalization which is going to be used for this conjecture. But of course, since it depends on a choice, somehow this choice has to be reflected in the situation. Because if we make a different choice, this normalization is going to change. So where is it reflected? Well, it's reflected here in this conjectural picture. So here we have the trivial representation, and here we have a priori no representation that stands out. And the expectation, or what should make this consistent, is that this trivial representation goes to a representation here, which has the property that this character which we chose occurs as a quotient. That is, this representation is what is called B psi generic. And this is a definition of the representation being B psi generic. Okay, so now we're done explaining what. Huh?
Maybe more than one?
Well, one expects that there is precisely one. One expects that once you fix the Whittaker data, there is precisely one guy in the L packet. I'm only talking about tempered L packets, by the way. I didn't say it in the beginning, but this I'm only because everything is about tempered L packets, tempered parameters. But I mean, okay. Anyhow, I mean. Anyhow, I mean, okay, I guess I didn't have to say that because I already said we're only talking about suprcuspidal representations. But every now and then, if I didn't say that, and then people would remind me that I'm only talking about tempered. But anyhow, the L packets are now suprcuspidal. But of course, this whole business is expected to hold more generally for tempered L packets. And in fact, the L packets that we'll be talking about when we talk about theorems rather than conjectures are going to satisfy this principle that there is precisely one generic representation once this is fixed. So this is still only just conjectural. And before I go to say what the results are, I want to say a little bit more conjectural stuff, namely what happens if we now don't want to assume that G is quasi-split, but we want to talk about inner forms. Okay. So if G is not quasi-split, it's going to be an inner form to a unique quasi-split form. So we fixed our quasi-split form already, namely the G that we're assuming quasi-split. So it's enough for us to now consider all possible inner forms of that fixed G and see what happens with them. So let say G prime psi be inner to G, and by this I mean that psi goes from G to G prime. That's an isomorphism defined over F bar, and psi inverse sigma psi is an inner automorphism of G for every sigma in the Galois group. By the way things are set up, the L group of G prime is the same as the L group of G. So every time we have a Langlands parameter for G, it's the same as a Langlands parameter for G prime. Endoscopic data are the same. And so we would expect that a Langlands parameter would give us an L packet. We'll have a nice parameterization of this L packet. And we'll have the corresponding transfer conjecture also for these L packets. Now the trouble with this is, though, that the notion of an inner form is not rigid enough to allow for this to happen. I guess the first person that I'm aware of who observed this was Vaughan in his work on real groups, who then saw that inner forms have automorphisms which disturb the inner structure of L packets. They move things inside L packets around. And so he saw the need to rigidify the notion of an inner form. And he created two rigidified notions, the pure inner form and the rigid inner form. And a rigid inner form doesn't work for p-adic groups, but pure inner forms do work very well. And so let me say what a pure inner form is. But before I say that, you can also see the problem on the geometric side. Namely, we talked about how it's necessary to pick a specific normalization of the transfer factor in order for things to make sense. And there is no way to do this on a general inner form. You need an additional data to allow you to do this. And so a pure inner form adds one more bit of data to this. So it's going to be a triple with where this is as before, just an inner form. And the Z is going to be a one cocycle for the Galois group in G, which captures this thing here. That is psi inverse sigma psi is given by the inner automorphism given by this particular element. And so inner forms, so here inner forms up to isomorphism, they're parameterized by H1 of G in the adjoint group, G mod divided by the center, and then pure inner forms up to isomorphism are just classified by this. And the reason I'm saying this is because, and the way you unpurify a pure inner form is just forget this data. You get a map from here to there, and that gives you the pure inner form. The reason I'm saying this is that, just as a remark, you just look at what happens when you take a inner form, a pure inner form, and forget that it's pure. And this map is going to tell you, or the image of this map is going to tell you which inner forms can be purified, which inner forms come for pure inner forms. This is not just an additional data that rigidifies, unfortunately, but the existence of this data is actually a condition. Or in other words, this map is not surjective, which is unfortunate because you would like to, for whatever I'll be saying in a minute, to take into account for all inner forms, but it doesn't. It only takes into account specific inner forms, and in particular, somehow the worst case scenario is when G is simply connected. When G is simply connected, Kneser tells us that there is nobody here. So you cannot purify any inner form. And this is the starting point of a very interesting story. What do you do to get the rest of those things. And I may or may not get to this today, but you can actually do something about it using the theory of isocrystals with additional structure to as a replacement for this set of pure uniforms. But the good news is that whatever I'm going to say now about pure uniforms goes through with little modification to the more general case. And both the conjectures and the results and so now here are the conjectures. So what can we do with such a pure uniform? So if we have a pure uniform, this is the central point, which was an observation of Kottwitz, that the purity of a pure uniform allows you to extend transfer factors canonically across different uniforms. So if you have a pure uniform, and if you have chosen, if you have already chosen such a transfer factor on the quasi-split form. So you found some way to choose it. For example, you've chosen it with respect to Whittaker data so that it works well with the character identities. Then what you get is an extension of this transfer factor, which works for both the quasi-split form and the pure uniform at the same time. And the reason I'm putting those two together rather than saying, oh, then we get something which works for this endoscopic group and the uniform, is the fact that the transfer factor here and the transfer factor here are actually related in a good way. And the way this works is it makes sense to say what it means for an element in here and an element in here to be stably conjugate. So you can actually enlarge the notion of stable conjugacy. This is very simple. You just, where is it? There is the homomorphism. You just take gamma, push it with this homomorphism over, and just it's not going to be an F point anymore, but you will not care about this. You'll just ask, is this point which you have here F bar conjugate to this point? If that's the case, then those you call them stably conjugate. For this you didn't need the purity of the pure uniform. You can just do it. But what you need the purity of the pure uniform is to measure the relative position of those two elements. There is this invariant that pops up all over endoscopy that it's crucial for this theory, and it measures relative positions of strongly irregular semisimple elements in a given group which are stably conjugate. But now you can form this invariant for elements of those two different groups, and for this you need the Z. And once you need this, then there is an obvious formula you can write down which gives you at least a candidate for a transfer factor. And I'll say in a minute what I mean by candidate. But at least we have this function now. And so what we can do is we can form the disjoint union over all possible pure uniforms. This will be a finite disjoint union of groups. And we can extend this transfer factor, which is Whittakerly normalized at the quasi-split form, to a transfer factor for this whole thing here. And with respect to this normalized transfer factor, we can now say what the conjectural general picture is, and that is the following. We're going to, so what we're saying now is how to parameterize L packets on all inner forms at the same time, or at least all pure inner forms. And how we're going to do this is we're going to take the centralizer of our Langlands parameter in G hat, and we divide it in the beginning by the center of G hat gamma, and we're not going to do this now. Then what we expect is a bijection between the irreducible representations of this finite group and a compound L packet, which is a disjoint union over L packets for each pure inner form. And moreover, this bijection is going to satisfy the following compatibility. When we have an irreducible representation of this, we can restrict it so we can restrict it to this group, because the gamma fixed points of the center always embed in here. They centralize everything possible, particularly in here. We pass to pi zeros, and then we can take an irreducible representation here and restrict it to this. On the other hand, such a compound L packet, each individual element tells us over which possible pure inner form it lives. We just project every element in here to U. And there is an isomorphism here due to Kottwitz, which identifies this and this. And so the expectation is that this commutes. And now everything is peachy, because we can again form these unstable combinations. Every time we have an element in here, we can form a corresponding linear combination, just like in the beginning, but within any possible L packet. Let me just write this. So now what we can form is, for every pure inner form, we can look at the L packet on that pure inner form. That's the pi phi U. And we can form this object where we take irreducible representations of pi 0 C of phi, but only those which are responsible for the particular pure inner form, where the rho maps to U under this map here. We can form this, and the conjecture is again the same, namely that we have this same relation as we had before. Okay. So now finally we can I can say what the results are, and then I'll take the last 10 minutes to try to give a rough idea of the proof. And for this, I'm going to use the computer. So can we let this down, and but without turning off the light? And
So this H1 of Fg, you can repeat the same. I mean, you can have a repetition of the same inner form.
Yes. Well, so there are two things. I don't know exactly which of the two you're asking about. The first thing is that, of course, we have modded out by equivalence, which means that two different cocycles can map to the same, two different pure inner forms which are isomorphic, they'll map to the same U. That's one thing that you may be asking. Or you may be asking about the non-injectivity of this map here. Yeah. That's what you're asking about? Yeah. Yes. Well, that is precisely somehow the desired effect. We couldn't normalize things properly before because we had automorphisms of each inner form. And now we avoided this problem just like you avoided when you do moduli spaces of things and your objects have inner form. You put some additional structure, and then you have different objects which are going to have different additional structures, and you treat them as different points. And you do the same thing here. You have different inner forms. You have the same inner form that can be rigidified in a different way. And you treat those in a different manner. And what will happen here is that you will have, every time you're looking at two different U's which map to the same element in the cohomology of the adjoint group, you have a non-canonical bijection between these L packets, but there will be no reasonable way for you to actually choose one. And so that forces you to treat them differently if you want to parameterize them in a coherent way. So they will be treated differently. And those things here, those things here are going to end up being the same up to some non-zero complex root of unity. But you cannot prefer one over the other or try to identify them in a reasonable way, because the same difference in normalization is going to be reflected in the transfer factor for the different purifications of the same inner form. You have this transfer factor here, if you have the disjoint union over different pure inner forms which correspond to the same inner form. If you look at what happens to the corresponding restrictions of the transfer factors, they will basically the same function if you identify them non-canonically up to some scalar, but which you cannot fix. So this is indeed a rigidified data that you pick on top of the inner form. Does that answer the question? Yeah. Okay.
So for torus, for example, so what's the for torus?
A torus is too simple to actually worry about. I mean,
But the part in H1 is not so.
Yeah. Let me think about it when not everybody is staring at me. It's a very, very simple thing, but it's. Yes, yeah, it is. It is. So I'll answer your question just, and I want to say the things I want to say, but okay. So I'll say them here. So the first thing is. So DeBacker and Reeder in a recent paper have considered Langlands parameters. Oh, I'm sorry. Is this at all a good board to write on? Okay. So they've considered Langlands parameters of the same kind that we mentioned, but with the additional properties that. Okay. So let me write this. This is G hat semi-direct product with WF, and I want to write the first component as phi 0 of W and then W. And the ones that they considered are those where phi 0 of wild inertia is trivial and where the centralizer of phi 0 of inertia is a maximal torus. And these are what they called tame, regular, semi-simple, elliptic Langlands parameters. Trselp, it's easy to pronounce. And so for those, they've constructed all the things that we talked about. They've constructed an L packet on each pure inner form. Sorry, and G is unramified. So G is the quasi-split form, and we assume that it splits over an unramified extension. And for this group and all its pure inner forms, they've constructed L packets which consist entirely of depth 0 supracuspidal representations. And they have constructed the parametrization, and they've also shown that each individual L packet is stable. So okay, and now the theorem, although those were of course all theorems, but the theorem is that in this situation, the endoscopic transfer holds for whatever endoscopic triple when you have a pure inner form here and such a Langlands parameter. Okay, and I have a few minutes to talk a little bit about the proof, how this works. Here it is. So is it visible or necessary to dim the lights, or is it good? Okay. So the first is a very simple thing which goes immediately, and it's we have an equality of distributions that we'd like to prove, where we have this distribution evaluated at f is equal to this distribution evaluated at f upper h. And one can just take the Weil integration formula and reformulate it in terms of functions, which is nothing spectacular, but it's just useful because characters of p-adic groups are usually given in terms of functions. And so what happens, which is a little bit curious, is that in this formulation, which is equivalent to the previous one, at least to state this equality, you don't need the theorem that the geometric transfer exists. You don't need the theorem that tells you to every f there is an f upper h, just for the statement. And of course, the f upper h got untangled because these things appeared here. Okay, but still this theorem is going to be immensely important for the proof. And not just the theorem, but all the theory that went into the theorem. The next thing you do, I guess we don't do anything else. Isn't the arrow here supposed to? Isn't the arrow here supposed to change? Should I point anywhere specific? Ah, I thought it's a remote. No?
Good.
Okay. Wonderful. So the next thing we show, I said you can, using the purity of inner forms, you can construct a candidate for a transfer factor. Well, you actually have to show that your candidate is a transfer factor. And what makes a transfer factor is that its quotient is the canonical relative transfer factor constructed by Langlands and Shellstad, which does not depend on any choices, but it's relative. And so originally when Kottwitz came up with this formula, he thought about how it works in the case where the center is connected to the group. And then it follows by standard arguments from the lemmas which appear in the paper of Langlands and Shellstad on transfer factors. But what happens funnily is when the center is not connected, this breaks down and the thing becomes much more subtle. And I just want to give one little kind of idea of what goes into this, because it's I find it a little curious. So let's take any maximal torus in our group whatsoever, and let's take any other maximal torus in our group whatsoever, and they're defined over F, but they're unrelated. They're not stably conjugate, they're just any maximal tori. And we can look at the preimage of those two in the simply connected cover, and then we also have the center of our group and the preimage and the center of the simply connected cover, and those two maps are immediately seen to be quasi-isomorphisms of complexes. And what this gives us is a canonical isomorphism on Tate cohomology. And the question is now, describe this isomorphism by a formula in terms of cocycles. And the reason you want to do this is because you want to do diagram chasing and compare two Tate-Nakayama pairings, one occurring here, which is kind of a relative thing, and one occurring here, which is a product of two different ones. And the way one does this is, well, we take an element in G which conjugates this torus to this torus. It's going to be defined over F bar. This gives us a map on complexes, but this map is not gamma equivariant. And the curious fact is that its failure to be gamma equivariant is homotopic to 0. That is, it's somehow gamma equivariant up to homotopy. And what this ends up giving you is that, and moreover, the homotopy is unique. And using this particular homotopy, you can write down a formula which goes from here to here. But the curious thing is somehow it's not the standard thing where you have two maps preserving all structures which are homotopic and they give you the same map on cohomology. Rather, you have one map and it doesn't preserve all the structure. It preserves it up to homotopy. But it still somehow ends up giving you not only these isomorphisms, but they also respect cup products and they respect duality and everything you need. So it's a curious fact. But then we actually come to proving something. And so this is one side, the unstable character that we would like to relate to the other side. And what one does is one has to find the reduction formula for this thing here with respect to the topological Jordan decomposition in our p-adic group. So the gamma will be a strongly irregular semisimple element, and when it is compact, which means contained in a parahoric, then you can find something similar to the Jordan decomposition, which actually in the reductive quotient over the finite field corresponding to this parahoric actually projects to the Jordan decomposition downstairs. And the reduction formula looks like this. I'll just explain a few bits. There is a certain plus minus sign, and then we have a double sum where p goes. So we fixed a Q0 in the Lie algebra of G. That's going to be our the fixed thing that everything will relate to. And then P runs over the stable classes in the centralizer of gamma S of elements which are stably conjugate to Q0, and Q runs over rational classes in the centralizer of gamma S of things which are stably conjugate to P. Then we have a certain character which is a data coming from the Langlands parameter. We have this invariant here that I talked about, which measures the relative position between Q0 and Q, and it's paired against the endoscopic character. And then we have the Fourier transform of an orbital integral at Q in the Lie algebra of the centralizer of gamma S. And we want to do a similar thing with the right-hand side. And because the stable character is basically a special case of the unstable character, we have this formula immediately there. But what we have to do is reduce this part here, which means relate this endoscopic group for G to an endoscopic group for the centralizer of gamma S in G, and these transfer factors. And this was done by Langlands and Schellstadt. This is the theory of descent for endoscopy. There was additional work of Hales in the unramified case. But one has to be careful when centralizers are disconnected. What this ends up being equal to is the following. And again, we have some signs here, and in here in particular is the epsilon sign, which is responsible for the Whittaker normalization. It's an Artin epsilon factor, which is corresponds to this Whittaker character, and to a certain virtual Galois representation, which tells somehow how the Galois action on the quasi-split torus on G and on H are twisted against each other. And then the Y's are stable conjugacy classes of elements which are related to the gamma S. And the Xi's are the different possible inequivalent ways to recognize the centralizer of Y in H as an endoscopic group of the centralizer of gamma S in G. When the centralizer in G is disconnected, there are multiple inequivalent ways to do so. And then we have this finite group here. And from here on, the formula kind of looks like the formula before, because it comes from this bit. And the reason, and one also has to, okay. The reason I'm saying all this is not just because it looks ugly, but because I want to then say what the actual input in the proof of this is. And so, so we want to relate this to this. And the way you do it now is, and here is the serious input that goes into this, is the following. If you look at, I can't sit here. Okay. If you look at this part, well, we're summing over rational conjugacy classes inside a fixed stable conjugacy class. We're taking this pairing here, and we're taking Fourier transforms of orbital integrals. So this is the Fourier transform of an unstable orbital integral on this Lie algebra. Whereas down here, we're doing something similar. We're summing over the rational class inside a stable class of these Fourier transforms, but we're not putting any weighting factors. And in fact, this thing is endoscope. It looks like something that's going to be conjecturally the endoscopic transfer of this. And this is now the crucial input. It's the Vautz-Bourget's theory on endoscopic transfer for p-adic Lie algebras, to which its crucial input is the fundamental lemma. And so all these things combined give you a huge sledgehammer, which tells you that this thing is the same as this thing up to a certain well-defined 8th root of unity, and which comes from the fact that the transfer relates orbital integrals to orbital integrals, but here you have Fourier transforms of orbital integrals here and there. And one of Vautz-Bourget's deep theorem tells you that if the orbital integrals are related, then their Fourier transforms are also related up to a certain specific sign. So this sign will pop out, and then you have to show that the sign that pops out together with all those signs becomes nothing. In particular, the sign in this specific case was a plus-minus sign rather than an 8th root of unity. And then you're left with relating this side to this side, and you do this by constructing a fibration, which a triple like that sends to P, is surjective, and its structure group is this. And once you have this and you do a careful bookkeeping and you look at everything you need, then you're done. Yeah, and I'll stop here.